All right, so we are continuing on in the next portion, and we will be developing our shear diagram. So first, let me just kind of erase everything so it's nice and clean. Okay. All right, so how do we develop the shear diagram? Now, the easiest way to see shear diagram is kind of similar to what we talked about with some of the forces in Y, is where all you see is vertical forces from your loading diagram, from above, loading diagram, with the additional information of the solved reaction. So let's identify what the vertical loads are, okay? So from left to right, just think of it as you're walking along from left to right on this beam, right? And then think of it, all the numbers that are acting in the vertical direction, which is either up or down. Maybe it's a weird elevator. Let's call it the weird elevator. Okay, so let's see what that means. Let's see how that translates. Okay, so you start at point A, right? Let's kind of draw us back in there. Okay, and I'm going to travel from here all the way to the end. So the question is, what is the vertical load doing to me as I'm walking from left to right? Okay, and that's kind of like the key component that we got to think about. So here I have 133.75. I take the elevator up, right? And 40 kilonewtons per meter. Now that's a vertical load, but it's stepped per meter. So it's 40 kilonewtons per meter. So you can think of this maybe as an escalator, right? Because an escalator kind of goes downward like that, right? And you're traveling 40 kilonewtons for every meter that you walk. So from for that 8-meter distance. And so you kind of travel in that direction. And the total elevation change would be 40 kilonewtons multiplied by 80, which is your resultant force of 320 that we drew before. So if you start at floor 133.75 and you go down 320, we're kind of underground right now. So that's going to travel you down that much-ish, right? And then when you hit point B, it says that you have an upward reaction of 206.25. So now we're down a certain amount, okay? And this is taking the elevator right back up. And do you see anything from here? If you're right here, and as you walk right here, do you see any vertical load on you? No. And the only vertical load that you see is at the very end. So in your diagram, you travel here to here. There's no change until you get here, and it tells you to go down. So naturally, without even calculating this, if everything's all done correctly, I know that this point right here is 20 because you have to go down 20 and we have to close a moment diagram, right? And we always close our moment diagram. We always close our moment diagram, okay? So that's, sorry, not moment diagram, our shear diagram, okay? So what does that really look like in a shear moment diagram, or just shear diagram? 133.75, we go up. Remember, we took the escalator down. We took it right back up. Oops. We took it right back up. We hit that point, and we came down. There's that 20. The one thing that you'll be asked as you do this, I know that this is more simplified approaches, and you should know this, is that when this escalator, as you travel, when do you hit ground level? Right? When do you hit ground level? Well, there's many different ways to do it, right? It's just a mathematical understanding of what it is. You have a certain slope, you have a certain y offset, and then you come down. And so at what point do you do that? You could do similar triangles. You know, I like to kind of do this stuff. X is equal to 133.75 divided by 40 is equal to 3.34. So that means, what is my x direction travel? Okay, when I start at 133.75, and as I travel at 1 meter approach, and 1 meter, I travel 40 kilonewton ground, 40 kilonewton ground. So how many of these do I need in order to equate to 133.7? Well, that's 3.34. And so you've got to know where you're starting with, right? You do all those calculations, and it would be such a waste that you put that value over here when it's really meant to be here, right? Because you're starting from this point and going that way, okay? Okay, so next, right, what do we do? Okay, what do we do? Well, let's go back to our handout, and in terms of what we do in terms of steps, and let's go back to here. Okay, so as a review, it says, develop shear diagram. What is your vertical force doing? Shear diagram closes on both sides of the ends. Use transformation chart, which we did. Remember the point load right there. Downwards means down, up means up in your shear moment diagram. Distributed load, we talked about the escalator. All right, we're good. So now we're going to go ahead and develop the moment diagram. Okay, moment diagram based on the area of the shear. Okay, area of the shear. Okay. Positive shear is addition, negative shear is subtraction, okay? Max moment and minimum moment is where shear is equal to 0. Do you see naturally when this 0 stuff occurs, it's such a big deal? And mathematically, when we're taking integration, integral, you know, and finding where the value is, you knew that mathematically that meant that it meant the maximum, the minimum, or the minima, or the maxima. And so that same mathematics correlate and corresponds back to a shear moment diagram because, you know, it's all related. And finally, a moment closes at 0 on both ends unless it's a fixed wall, because the wall will carry that last moment. And so if you take the wall reaction and apply it at the end, you'll equate to 0. So everything closes at 0, ends at 0, and that's statics, right? Because statics is all about just balancing one point to the other point, right? Okay, enough of that. And so next, what we'll go over is the moment diagram.